recorded. Should I explain from scratch for the sake of recording?
Yes, sir, you can continue. No problem.
Should I simulate from scratch or not? Okay, I'll just continue. I want to mention again about the important part. So far, I just build a rectangle by right-clicking on the geometry, and after that, I add the piezoelectric edge as a piezoelectric materials. Under the solid mechanics, I need to change the direction of the polling direction by changing this. And in the definition section, COMSOL has provided us two different coordinate system, that one of them third direction of the first one is aligned with the R direction, and I will choose this material ZX instead of material XZ. I can change it from this feature piezoelectric material. I also need to add boundary load by right-clicking on the solid mechanics and just simply select the inner boundary and change the load type to the pressure and type 0.1 megapascal. Also, I need to constrain the bottom surface by choosing roller instead of fixed constraint, because I still need the movement in the R direction, so I just constrain it in the normal direction. Okay, now I move on to the electrostatic part and choose the ground and assign the inner and outer boundary as ground. I also need electric potential for the second study, and I will disable one of them, actually electric potential in the inverse effect of piezoelectric. It's better to assign the inner boundary, and I apply 1 volt to the inner boundary. In the multiphysics part, the COMSOL has coupled the equation of solid mechanics and electrostatics, and I just finished the setting the boundary condition of my material. In the solid part, I just add the boundary load, pressure, and the roller. In the electrostatic part, I add the ground and electric potential, and I assign the two. But when we add the electric potential, since they contradict each other, the electric potential will override the this actually boundary that we have applied ground before. But when we disable here from the study, it will again active. I skip the mesh part because the geometry is simple. COMSOL will mesh it for me. In the study part, I go to the step 1 stationary and tick the modify model configuration for study step. Now, when I want to apply a direct effect, I should disable one of the boundary condition. Can you tell me, please, in the chat section, what boundary condition I should disable for the direct effect in which the electric potential will be output of the simulation? For the direct effect, I want to do analysis. No comments, anybody? I repeat my question. What boundary condition I should disable in the study to see the direct effect of piezoelectric in this example? Because I already apply both boundary load and electric potential, and this means that these two are driving the system. But I need just one of them to drive the system, either a boundary load or electric potential. Okay, no comments. For the direct effect, since the electric potential will be output of the simulation, I need to disable here because it will be the output, not input, simply by right-clicking on the electric potential and disable it. Okay, now, if I haven't missed anything, COMSOL can compute this example for me very quickly. Actually, in this example, we say that the pressure that we applied on the inner boundary will produce electricity in my tube. And I will show it by electric potential in the result section. Here, we can see the stress on the tube due to the applied pressure. Also, we can see the electric potential here due to the applied pressure. You can see that the left boundary and the right boundary have zero voltage since we have added the ground for the direct effect on these two boundaries. Now I want to add another study to show the inverse effects of the piezoelectric. Here I need to add another study, stationary. I add it from the add study and it come in the study number 2. Again, I need to modify model, but this time I should disable the boundary load since I need electric potential to drive the system. So I disable this feature, but I keep electric potential. In this case, the ground will apply to the right side. When these two are enabled, the ground will apply on the right boundary, and the electric potential will apply to left boundary. Now I just simply compute the model. And by applying these to a study, showed you how to simulate those inverse and direct effects. But in the inverse effect, the stress is due to the applied electric potential, not the boundary load. And here we have made a sensor. It can be a sensor of pressure, and when the pressure exceeds the threshold, we can realize it from the output signal. Okay, any questions so far? Okay. For you, if you have any question, please ask me in the chat section, not by your microphone, because my headphone is unplugged. Actually, I turn it on, but after time, it gonna turn off. Okay, no question. Thank God. Now I want to show you an important issue in the COMSOL multiphysics. Actually, in the time dependence. So far, I did a stationary study to see the stationary response of COMSOL. But what if I want to see the transient response of the system? What should I do? I can add a time-dependent study, but it needs some consideration. If you don't care about some details, you will get an error. I want to show you how to solve the error when you switch to the time dependent, and it's a really common problem in applying a time dependent. I want to apply a direct effect, so I keep the boundary load, but I disable the electric potential. Okay, I change the last time to 10, and I press the compute button. You see that I got error. It says that
fail to find time steps so that given tolerance are satisfied. Time 0, last time step is not counted. What should I consider in applying transient analysis is that we should actually simulate what happened in reality. When you are applying this problem in practice, you don't start your experiment by applying your pressure from scratch. You may probably increase the pressure gradually, and we should do so in our simulation. Otherwise, the COMSOL will not converge. So what should I do to apply a gradually increasing pressure for my simulation? Any idea? Please tell me.
So you can add a step function.
Yes, it's true. We need to apply a function, but I don't apply a step function here. I want to add a ramp function. Both of them are correct, but here I want to apply a ramp function. Thank you very much. And you should do some trial and error to see what type of function with what details can give you a convergence. Here I define a slope of 0.1 with the cutoff of 1, and when I plot, I can see that I have something like this for my pressure. But I multiply it, I can rename it to pressure, for example. I multiply it to the previous amount of my pressure. I type pressure. I should respect to the notation and type like this. And here I just apply a gradually increasing function by defining a ramp function multiplying by 0.1. And our plot is something like this. And I want to compute it from 0 to 10. Now I press the compute button to see if COMSOL can converge or not. Now, fortunately, COMSOL could converge, and it gives us some results with respect to the time, and you can see the transient response of the model. In any time you want, you can select just the time and see the results that are similar to the previous study. Also stress and electric potential. I also can add a new result. For example, 2D, since we are applying, we have a 2D axisymmetry, but if we want, I can show the result in 3D state, since COMSOL can revolve the geometry of 2D axisymmetry and show the result in 3D by adding their revolution to the data set by default. I add a surface. I want to show you the displacement, and you should choose a right dataset, and from the surface, you have here the displacement, or you can select it from the solid mechanics branch, and from the displacement magnitude in meter, or for example millimeter. And the results are in millimeter, and you can see the displacement in my geometry. Now I want to apply third application of the piezoelectric, which is energy harvesting. It needs some more consideration to.
I have one doubt.
Okay, tell me.
So in that ramp function,
Okay.
You have typed pressure in bracket T for time, then in bracket 1/s. So 1/s for what purpose?
Actually, this is the notation that we should apply in the writing the definition of the function. Actually, by this, you are showing that this hasn't any. Actually, you cancel the unit of the pressure or T, and actually you show that the unit of the pressure is just megapascal, not second or anything else. Actually, you are canceling the unit of time by writing the inverse of second.
Okay, sir. Thank you.
Yes, this is just explanation for the why we write the inverse of the unit of input. Okay. Now I want to switch to the third application, which is energy harvesting. I need to add another
Physics. Any idea which physics I should add?
harvest energy efficiently. Actually, harvesting energy from a system needs some optimization, and you should optimize your, for example, geometry, or your material, or the circuit. And for energy harvesting, I need to add electrical circuit physics. Here, from add physics, I add from the AC/DC, and here in the bottom, I should add electrical circuit. Okay, but for harvesting energy, we should find the best range for our design to extract the maximum output of the system. By applying a Eigen frequency study, we can find the best resonance frequency here. And actually, for energy harvesting purpose, we should apply a frequency domain study. And before that, we should find the best range of frequency that system can give us for the maximum output. First, I set up the electrical circuit of my system. I just need a resistor and a ground for establishing the my electrical circuit. But before that, I want to define a resistance parameter to make it easy for us to sweep over this parameter. I start with the 10 kilo ohm here. Oh, sorry. Here, our underlying road as electrical resistance. And now I copy it, and I'm gonna add resistor from here by right-clicking on the electrical signal. But you should pay attention to the node names, because in the electrical circuit you are establishing your electrical circuit and you are connecting different components by simply assigning a correct node names to P or N. I type here 0 to connect it to the ground node, which was also 0. And here I type our underlying road as resistance for the circuit. I also want to connect the electrical circuit to the electrostatic part. For the energy harvesting application, you should add an external terminal from the external coupling. And again, you need to change the node name to correctly connect your components. The next point that I should add here, an important one, is that I no longer need the electric potential, but I need a terminal, because in the electric potential, you have no choice for selecting other type of terminal, but in the terminal, you can see that here in the terminal type, you can change it, for example, to circuit, and by this you are connecting your electrical circuit, and also you should apply the left boundary for this terminal feature. And here in the external terminal, you should change this to the terminal voltage. Now, we have simply set up our energy harvesting system. Again, I emphasize that our system is not optimized for harvesting energy. You should optimize your system in terms of different input parameters like geometry or material or your circuit. But here I just want to show you a simple energy harvester. And as I just mentioned, you need to first apply a frequency domain for the region frequency study for finding the best performance of your system. I need to deselect the electrostatic and electrical circuit because region frequency is just, I want to analyze it in terms of structural mechanics. And I press the button if I haven't missed anything. I should. Okay, I need boundary load because I want to harvest energy, for example, for the flow flowing in my tube. So I keep this boundary load. Okay, I compute. Now I can see the 6 different region frequency that COMSOL has computed for us, and it's about 800 kilohertz. I use this value for applying my main study, which is frequency domain. I want to strip through the range of the frequency by adding a frequency domain. Here I change it to kilohertz and I type 800 aspect of 10 and top is 900 and replace them. Okay, now I need to disable the electric potential here, since the boundary load will drive my system, not electric potential. And I also need the terminal to be connected to the electrical circuit part of my simulation. And again, if I haven't missed anything, it should converge correctly. I press the compute.
Okay, the problem is that we are applying a frequency domain, but we have here a function of t. I should remove this function, and also it's better to disable this function from the definition. Now again, I should compute it. Actually, the COMSOL in the frequency domain compute the full-time harmonic for us. So in this time, we don't need to gradually increase because we are not solving a transient analysis, but frequency domain. Now, we can see the results of our fifth study that is related to the energy harvesting. And we can see the results in different frequency. The amounts are different. And if I want to see where the maximum output occurs, I should add a 1D plot for my analysis. I should add a 1D plot here. I need to do it globally because it has something to do with the whole of the system, not any local point. Change the data set to a study file. Here I need to add expression. I want to see the voltage across the resistance. Here I can add it from here. I want just to see the magnitude, so I apply a apps operator. I also can see the power by dividing it by r. Actually, I should power of 2 and divided by r. It is the definition of the output power. You can see that its unit changed to the watt. And if I press the plot, I can see that the maximum of the output occurs on the 880. So I can use this frequency for my next study, which is optimizing the resistance. Again, I add study because I already found my best frequency. I add frequency domain, change it to kilohertz, and I just type 1 frequency. Also, to find the best electrical resistance for my system, I should sweep over this parameter in the study set extension by activating the auxiliary sweep and adding the only parameter. I can add a range here from 10. I step up again 10 to, for example, I change the unit to the kilo. Again, I should see that if there is any boundary condition, should I disable it is electric potential. And okay, I press the compute to sweep over the parameter. Actually, by activating this option, we are telling COMSOL that compute our system with respect to these 10 electrical resistance. And I can do similar work for our new parameter, which is electrical load. Again, I added the 1D plot. I changed the data set to the study 6. I again add the global. Actually, I can copy this expression and paste it here in the y-axis data, and in the x-axis data, COMSOL correctly selected our desired parameter, which is our underlying load. I just plot, and you can see that by increasing the resistance, the output power will decrease. And so we should continue this process to find other optimized parameters. Please pay attention that if I want to optimize our parameter which are related to the geometry, I don't have to use auxiliary sweep that I did for resistance, but I should add a parametric sweep from right-clicking on the study and adding parameters. This is used for the parameters related to the geometry and the mesh. Okay, any question?
Sir, how to know how much energy in watts generated by this energy harvesting? How to calculate total amount of energy generated? Hello? Hello? Hello, sir?
Now I switch to the PowerPoint.
Hello, sir? Am I audible?
I just want to show you another type of piezoelectrics, which is transducer, piezoacoustic transducer. You can talk about the piezoelectric devices without mentioning the acoustics, since in many applications you should include the acoustics physics. The main or the typical physics of acoustics in COMSOL is pressure acoustic, which is used for propagating the wave in the fluid domain, like this geometry that I'm showing. For applying a piezoacoustic transducer, I should add two rectangles, one for piezoelectric disc and one for the membrane, which is matching layer, and it's used to improving the propagating wave. Also, we can actually this is a cylindrical simulation. It has a rotational symmetry, so again we can take advantage of 2D axis symmetry in COMSOL multiphysics. I switch again to the COMSOL. Sorry if you have asked question. My
Phone I didn't hear since my headphone had turned off. If you have question, please ask me in the chat section.
If any participant is having any question, please ask in the chat box.
Hi, sir. Actually, in the result, we can see different type of energy from here. If you have the equation for the total energy, you can use it, but also you can use total energy from here under the electrostatic part. This is a total electric energy. Also, you can add any loss to the piezoelectric material or linear elastic. Since we have only one domain for our piezoelectric, you can add any type of loss, and after the computation, you can see the waste loss due to the mechanical damping or any other loss that you have added in your model. Actually, the second thing that I mentioned was about the wasted energy, but the harvested energy is the thing that I just showed, and I think that it is the harvested energy that is across the resistance. But I said that this is not the optimized circuit. You can add different components to harvest better. Okay. I want to start the second model, the piezoacoustic transducer. Again, I go through the model wizard, to the axis metric. This time, I should include the acoustic part in my simulation under the acoustic structure interaction. And from here, I choose the frequency domain type of my physics. I add it, go to the study and select the frequency domain from here. I save the previous model. Now, we move on to the graphical interface of the COMSOL. Before starting, I need to define some parameters related to my simulation, which is the F min, the minimum frequency, which is 10 kilohertz. F max is 16 kilohertz. F step, which is the step of my study, which is 1 kilohertz. I need to provide velocity of the wave in the air, which is 343 meters per second. I need to define the thickness of my membrane, which is 0.4 millimeter. Thickness of the PZT, which again is 0.4 millimeter. I need to define the width of my PZT, which is 5 millimeter. Actually, this was for the membrane, and this is for the PZT, and is 3.5 millimeter. Also need the radius of my air domain, which is 20 millimeter, and the apply voltage, which is V0 and is 5, uppercase, 5 voltage. In the geometry part, I need to first add the air domain, which is circle, and I enter the underline air as the radius. And since we are modeling quarter of a circle, I need to type here the 19 degrees. I can rename it to the air. Now I need to add the brass membrane by adding rectangle with the width of R underline mem and the height of the edge underline mem with the position of the edge in the zip direction. I build it. Here you can see the brass membrane. Again, I add a new rectangle for the pivot. With the width of our underline pivot and the height of the edge underline pivot, and with the position of minus the edge mem minus the edge underline pivot. Okay, the geometry corrected build, and I need to tell what equation solve in which part before adding the material. Here for pressure acoustic, I just need sorry this circle. For solid mechanics, I remove the air domain, and in the piezoelectric, I remove this. Also for electrostatics, I just need the piezoelectric material. And okay, there is no need for changing the pulling direction, since I want it to be aligned with the Z direction, and COMSOL by default
aligned with the Z direction. So no need change.
I need to add materials from library. Recent material is good choice if it shows to me. P35H and air. I need to manually define the brass membrane. First, let's address the selection. This is the pivot. This is the air domain. And I add blank material for the brass membrane. With the Young's modulus of 100 gigapascal. Sorry. And the nu of 0.3 and the density of 8900. Okay, now I can change the fluid model of the pressure acoustic. Since I told you that the pressure acoustic physics is going to solve the wave propagating in the fluid domain. Here is air domain, and I can change the fluid model for my application. I can choose between these options. For now, I choose atmosphere attenuation with the relative humidity of 0.5. Okay. I need to truncate the open space since we can't simulate the whole surrounding domain. I need to tell COMSOL that truncate open space by adding a perfectly matched layer. Okay, I apply it to the outer boundary, and you can change the settings of the PML, but I leave it unchanged. You can study the difference between the different options here in the documentation of COMSOL, but here I leave it unchanged. Also, I need to add exterior field calculation to capture the results beyond my geometry. Since I mentioned that by applying a perfectly matched layer, we are going to truncate the open space, but we still can see the results beyond this boundary by adding exterior field calculation. Again, I apply it to the boundary number 11, and here I need to define it as infinite sound hard boundary here. Also, you can see the details in the documentation, but for these applications, we typically use these options, and the symmetry plane is z equals 0. Okay, I just finished the setting up of the boundary condition of pressure acoustic, and I go to the solid mechanics. I need to fix the boundary of a structural part, and I gonna choose this boundary as its constraint. Since in transducers, the electric potential drives the system, I need to define both ground and electric potential together. Sorry. I add the ground boundary to the boundary number 2, and electric potential. Actually, there's no difference. Sorry, I over. Okay, and by this, I just need to apply a voltage that I define in the parameter section, and the mesh part in the acoustic modeling should be carried out with full consideration. But COMSOL can do it for us, but we also need to do some operation on mesh part. As you may know, the modeling of the pressure acoustics in the mesh part, you should be assured that mesh can resolve the wave propagation, and you should do your mesh part with respect to the wavelength and frequency. Here, first I need to set up the frequencies of my simulation, and after that I go to the mesh part. Start from F min, F set, F max. I replace it. Here we have to explain some operation in the mesh. First, I need to deselect the all part except pressure acoustic and change it to user control to see the sequence of the operation that COMSOL has provided us for physics control. Here I need to apply a mapped mesh for a structural part. Actually, the meshing somehow needs some trial and error to achieve the best mesh. And since I don't need to focus more on the mesh part, I just show you how to do it, but you can study more in documentation or in the videos in the official website of COMSOL, comsol.com, and there are lots of videos to explain the meshing part. Here I add a mapped mesh here for these two domains. I right-click on the map and select the size. I change it to custom, and I don't want my maximum element size exceeds the minimum of the thickness of pivot or membrane. Okay, I actually need to tick this option, and I will show the effect of this effect of this option when I create the mesh bit and without this option. Now I build all to see what happens.
Okay, you can see that.
The mesh element on the structural domain is bigger than the part, and I can change the order of the operation to tell COMSOL that give the structural parts priority. Again, I build this, and I can see the mesh part change because the order is really important. And we can see that here we have a finer mesh because COMSOL tries to match the nodes on the interface. And now I want to show you the effect of clearing and activating. Please notice these elements. You can see that they are somehow distorted. We don't want the elements to be distorted because it will lead to incorrect results. Okay, now I need to do other operation to make the mesh elements on the structured part even finer. I right click on the map and choose the distribution, and I choose these two boundary and select for boundary element because I want to have two elements in Z direction for my structural part. I should apply this on the mesh, and here we can see that we have a better mesh compared to before. Now I can just compute to see the result if I haven't missed any option. Now we can see that the electric potential will drive the system and deform the piezoelectric material and the matching layer, and shows the displacement here. And this displacement, because of the acoustic structure boundary and the interaction, will transform to the air domain surrounding air domain. And here we have another another multiplicity for coupling the solid mechanics and electrostatics that's applied on the shared domain. Now I click on the compute to see the results. Okay, for avoiding waste of time, I now switch to the PowerPoint, and after computing, I will return to the COMSOL. I want to show you another application. Sorry. Is it heavy for my laptop to run those COMSOL computation and PowerPoint? Okay. Here I want to mention an important application of transducer piezoelectric, which is non-destructive test. Here we again, I just mentioned this example via the slides because I think that we don't have enough time to completely cover the example. We can use the transducer to detect the defect within the material. Within the material, and we can infer it from the output signal that received on the boundary of the piezoelectric. Here we can see the graphic results, and here we can see the 1D plot. I switch to the COMSOL to see the result of previous simulation. Now we can see the distribution of the pressure in the air domain, and also if we add a height expression, we can have a better understanding of the distribution. Here we can see the distribution with the advantage of height expression. And I need to just tell you an important result, which is different from the other previous simulation, is that I need to add 1D plot group. Okay, for seeing the result beyond our geometry, I need to add a global equation and type this equation for the expression part. If I type it correctly, it will replace the value that I provide into R and Z. I want to see the result on the Z axis in the height of 1 meter in the decibel, and I can plot it, and we can see that somewhere between 30 and 14 kilohertz, the sound pressure shoots up and then decrease to somewhere around 55 decibel for 16 kilohertz. And here actually is the pressure sound level outside of the our geometry, because I added the exterior field calculation to capture the result outside of the boundaries. Now I see better. It is better to turn to the slides to show you another application. I will explain briefly in the PowerPoint. I think it's better to introduce you to another application instead of focusing on the result of the application. My laptop is somehow okay. If I could make it, can you see my PowerPoint?
Run through the slides. I said that you can use a transducer to detect the different material
by applying a voltage, driving voltage in the piezoelectric, and capture the reflected wave, actually the pressure that we receive on this boundary. And by comparing these two signals for with effect and without effect, we can extract the detail about this effect. But it has to be actually, you should consider some consideration for applying this type of test. I mean the angle of the wedge and piezoelectric. I need some care. For this simulation, you should add elastic wave, since we want to capture the wave in the solid parts, or instead of the fluid part. I said that if you want to see the result in the fluid domain, you should use the pressure acoustic. But if you want to see the propagating wave in the solid part, you should use elastic wave time explicit, specifically for this type of simulation. Also, you should add electrostatics and electric circuit. It is wrong. We should add the electrical circuit for applying a voltage source, because we need to provide a unique function for the driving voltage, not the constant. We should apply it with respect to the time. This is a sample, one example of driving voltage that we have defined in the analytical function. This is the damping material. Here is the transducer, and it is the matching layer. This is a wedge. This is the test sample aluminum, and this is the defect. And this is the geometry in the COMSOL with the absorbing layer here, because we don't want the reflection from here. And we have added the absorbing layer here and here. It is something like perfectly matched here, but it has some difference with that. Here we have taken advantage of non-conformal mesh by using form assembly. You know that if you use form union geometry for your geometry COMSOL, match the nodes on the interface. But by using the form assembly, COMSOL don't do so, and this is very good for reducing the time, the computation and size, because the elements don't need to conform each other on the interface, but we should use the continuity, and we should add it in every physics to tell the COMSOL that we want the actually the continuity here in the interface. We tell this by adding this feature, which has this equation for destination and source. It says that the source and destination for the boundary curve should be similar. Also, we have to change the pulling orientation of the piezoelectric, since we have our piezoelectric isn't aligned with the Z direction. Also, it is a little harder than our previous example, because we should consider the angle also to define a vector current. Also, we can take into account the mechanical damping for our piezoelectric. We have different options for damping type, and here we have chosen the Rayleigh damp. Also, we should use the low reflecting boundary on this boundary and this boundary, and choosing the damping type PNS. I don't have time to explain this option. You can study in the documentation, and we apply the terminal and the ground on the top and bottom surface of the piezoelectric. Also, you need to add electrical circuit with 4 different components: ground node, voltage source, resistor, and external terminal. And here we apply the definition that I just mentioned. Do I have time or not? I want to mention some application of piezoelectric in biomedical engineering. Okay, I start talking about this. Recently, by using piezoelectric within the body, we have eased the some of problem of patients. For example, we can use different medical devices, cardiac pacemaker, nerve muscle stimulator, and physiological sensors to help the patient, for example, for overcoming the closed or narrow artery. But these medical devices need energy, and we should provide energy for them by different methods. One of the methods is the capturing energy from the organism around it, for example, piezoelectric, and also there is a triboelectric nano generator or electromagnetic generator. Also, they can use the energy by the chemical reaction that occurs in the body. Also, we can use light to transport energy to the medical electronic devices. One of the best way to transform the energy is using ultrasonic devices, because in this way you don't need to change the battery and do an operation for changing battery. Actually, all of these are helpful, but I think this is the one of the best way to applying energy, transforming energy to the medical devices. Actually, the example that I mentioned in the transducer can be used similarly for energy harvesting. You can add the electrical circuit, and instead of driving the system with the electric potential, you just need to apply a pressure in the air domain, for example, and give this function for ultrasonic energy. SN is a good example of this, and it utilizes the sensor, for example, a sensor for measuring the blood pressure, or the velocity of the blood. Also can use to measure the level of oxygen in the blood. But this sensor needs energy, and we can provide it by ultrasonic wave. And like what I said in the first of the presentation, the PVDF is a good choice for using within body because it's biocompatible. Okay, thank you all for joining us in this webinar, and I just finished the webinar. If you have questions, you can ask.
Please ask your question in the chat section.
Okay, thank you, Ali sir. So if any participant is having any question, you can ask in the chat section or chat box.
Ali sir, kindly share your email address so the participants can reach to you.
Okay. These are my two emails. One is my email for myself, and the other is for my website.
Okay, sir. So if any participant is having any question, you can ask in the chat box. Otherwise, we are at the end of this session.
About the question that one of the participants asked, it depends on the behavior of material, I think. We can't say, but off the top of my head, I think you can rely on the results of the simulation if the both materials have similar behavior. Some materials demonstrate linear properties and some demonstrate nonlinear properties, for example, with respect of time. This is just a thing that comes off the top of my head, but it is common that we can rely on the new results, I think. But actually, it's obvious that it's better to validate your simulation with the exact material. No need to mention.
Digvijay sir, can you close the session now?
Yes, thank you all.
Kare sir, you can give the vote of thanks.
Okay. So thank you very much, sir. Ali sir, you have given a nice presentation related to the
Thank you.
topic piezoelectric device and energy harvesting. So
Thank you,
under the
thank you.
1 week online FDP on numerical simulation and analysis with COMSOL multiphysics. So thank you, sir. And on
Thank
behalf
you.
of all Swedish College of Engineering, as well as on behalf of all the participants, we are very much thankful to Ali sir as well as all the participants. And
Thank you.
with kind permission, now I'm going to declare that today's first session is over. Our second session will start at 3 p.m. Thank you, sir.
Thank you all. Goodbye.
Thank you, sir.